Yeah. So thank you very much for the invitation. And I'm talking about joint work with James McPherson and Matti Stroinski. So let me first recall some sort of general results on Hochschild cohomology of algebras. If we have an algebraically closed field and we take a finite dimensional associative K algebra, then the Hochschild cohomology is the X algebra of A inside AA bimodules. And usually you compute the, so one standard way of computing it is using the bar resolution. And you can argue that that's actually the original definition and that will become relevant later on, but if we're over a field, then those are the same. And then there are some well-known results, namely that HH0 is just the center of the algebra, which is trivial if the algebra is simple. HH1 is the quotient of the derivations by the inner derivations. And HH2, you can also give a nice description for it, some kind of co-cycle, two co-cycle condition. And that controls the deformation theory, the infinitesimal deformations of an algebra. So now we want to look at, instead of looking at algebras, we want to look at finitary birepresentations. And so let me first tell you what it means for a category to be finitary. That's just being equivalent to the category of finitely generated projectives for a finite dimensional K algebra. And then a monoidal category is called multifinitary if the underlying category is finitary. And I mean, we have some monoidal structure on it, which we also have an identity, and these satisfy natural axioms. So it's just a monoidal category where the underlying category is finitary. And it's called multi-fiat if it's multifinitary, and in addition, it has adjunctions. So people might also call that a rigid monoidal category. And here's an example. If I take some finite dimensional K algebra, and I take the additive closure of the regular bimodule and the projective bimodule, then, as my horizontal composition, I just take tensor product over B, then this is always multifinitary, and it's multi-fiat if my algebra is weakly symmetric. Okay, so now let C be a monoidal category, and we can talk about algebra objects in C, which is just an object that has a morphism from A times A to itself, and a morphism from the identity to A, the unit, and these satisfy associativity and unitality. So a finite dimensional K algebra is just an object in the category of, an algebra object in the category of finite dimensional K vector spaces. Okay, and similarly, we can define right modules over an algebra. So it's just an object in our category, together with an action morphism that satisfies the usual module axioms. And then we have the category of right A modules, and we can look at the category of projective objects in there. And similarly, we can define left A modules and AA bimodules, and inside we can look at the categories of projectives. Oops. Okay, so from now on, we let C be a multi-fiat monoidal category, and then a finitary birepresentation is just another finitary category together with some monoidal endofunctor from C to the category of endofunctors of M. So in particular, every object of C acts as a functor on M, and every morphism in C acts as a natural transformation of the corresponding functors. And then very roughly speaking, these finitary birepresentations correspond to algebra objects in the abelianization of C, where we take the abelianization in which the projective objects are precisely the objects in our original category. Okay, so now let's take an algebra object in C overline, so which corresponds to a birepresentation. Then we can define the Hochschild cohomology again as just the X algebra of A inside the category of AA bimodules inside our surrounding abelianization of our monoidal category. And so the point of doing it that way and not taking the original definition via the bar resolution is that this way we get an invariant of the associated bar representation. But if we want to compute it, then we run into the problem that A might not be a projective object. So if we have an algebra over a field, then the algebra is necessarily projective in the category of K vector spaces. But if you just have an algebra over a ring, that wouldn't necessarily need to be the case if it's not free or projective over that ring. So then you would run into similar problems that the X algebra and the thing that you compute by the bar resolution doesn't coincide. And so this is the problem. If our A is not projective, then the bar resolution is not a projective resolution, so we can't use it to compute the X algebra. And then the solution is to work with a modified bar resolution, and that's where it gets a bit technical. But we can still say some things. So in the beginning, it's quite boring. So if we take an algebra object in our abelianized category, then HH0 can be described like this, which is precisely the center. Yeah, because if you think about it, if you take your categories to be K vector spaces, sure, then the identity is just K, and a morphism in the category of vector spaces from K to your algebra is just picking out some element in the algebra with the image of 1. And then this condition just says that whether you multiply by it on the right or on the left is the same. And then it's still true that if we have a simple algebra object, which is equivalent to saying that the category of finitary, the finitary bi-representation associated to it is simple, then the center is trivial. And for HH1, we again get exactly the same description as derivations modulo inner derivations, where again we just have to rewrite things in an abstract way because obviously arguing with elements doesn't make sense here. But there are examples of simple algebras which have non-trivial Hochschild cohomology, first Hochschild cohomology. And things get a bit more interesting if we look at second Hochschild cohomology. In order to compute that, we really need to write down a projective presentation. Sorry, there's a typo here. This was meant to be let A1 under A to A0 be a projective presentation of A. Then we again can obviously write the Hochschild cohomology as quotient of cycles modulo boundaries. But now normally, so if our A1 were 0, if A were projective, then we would just have maps from A tensor A to A with this condition with the first line for the cycles and with this first line here for the boundaries, and that would be precisely what we had before. But now we also have morphisms from A1 to A0, and there are some extra conditions on these, and in particular, these essentially give us that in addition to the usual Hochschild cohomology conditions, we also have to consider X, so the X algebra of A with itself in the category C over line. And so we can compute that in some examples, but not in very, I mean, you can't do very much because it gets very complicated very quickly. Anyway, that was what I wanted to say. Thank you for your attention.